Hello. So I want to talk briefly about a few things that help get you ready to get through this assessment that you'll subsequently be tasked with taking that pertains to ions and ionic bonds and covalent bonds. Now, ideally, there'd be kind of a demonstrative application, but I think this presentation is quick enough and brief enough that we should be able to still hit the key points that are important for you to understand ionic bonding and covalent bonding. Now we start by just recapping a little bit, and you'll notice that on the screen there's a periodic table. Periodic table has three different colors. You got your blue, your yellow, and your red. Each one assigned to a specific grouping. Your red predominantly is what the periodic table is made of, which is metals. Your metalloids are found in between, and then you notice that you have a group of nonmetals located on the side of the periodic table. Now, as it relates to chemistry and chemical reactions, most of these guys participate in some type of interaction in order to become stable. Now, in some cases, elements will prefer to lose or gain electrons. We'll also find out a little bit later that some will actually go through a process of sharing electrons as well. So, let's go ahead and get started. We're going to first look at some vocab. And when I say look at it, we want to give a brief synopsis of the vocabulary that you want to pay close attention to as I present them. Some of them I will definitely spend time talking about the definitions because I feel like it's pertinent. But the words we're looking at are atom, molecule, element, compound, valence electrons, monoatomic ion, polyatomic ion, and ionic bonding. Now, if we wanted to, we can go ahead and throw covalent bonding in the mix because we will address that, but I will define covalent bonding as well. So, let's first start off with the first four, and that's going to be about the element, the atom, the molecule, and the compound. Now, an element is basically a pure substance that cannot be separated nor broken down into simpler substances by means of a chemical reaction. Same thing means that you can't break it down. Now, when you look at an atom, it represents the smallest unit of an element that maintains the chemical properties of that element. And then you look at something that's a little bit different called a molecule. Now, a molecule pertains to a substance that contains two or more atoms that are connected by chemical bonds. And a compound represents a pure substance that is made up of atoms of two or more different elements joined by chemical bonds. So the latter two of a molecule and compound seem very, very closely similar when we're talking about them, but there is going to be a distinction that we're going to get into, and so we'll see that a little bit later in the presentation. First, let's start off by just establishing what a valence electron is. Now, a valence electron refers to the outermost shell electrons of an atom. Now, in order for a chemical reaction to occur, it's always an interaction between the electron as a subatomic particle. An electron does this, an electron does that in a chemical reaction. And whether it's covalent or ionic bonds, it's all about the electrons. Now, it turns out that for main group elements, you can actually predict the valence electrons, meaning the electrons that are available for a chemical reaction based on its location on the periodic table. That's why this image is provided. You'll notice that on this periodic table, there is the letter X designating any random element in that column or family. And you'll notice that there's also a corresponding number. Now, the number tells you the charge that occurs when that element gains or loses an electron to become more stable, and it also tells you roughly, what you should expect to happen when that change in electrons occurs. Now, in all, this first column here has a +1 charge, and that only happens when that element loses one electron and it becomes more stable. Now, that means that it has one valence electrons, one available electron that's capable of reacting during a chemical reaction. If you look at the second column, this guy has a valence of 2, and when it loses those 2 electrons in an ionic bond, it becomes +2. We skip through ignoring the transition elements, mainly because they have a propensity of having variated instances of different charges of maybe +2, +3. You can see there's going to be a myriad of different options for some of those elements. But when we look at this group of here, and remember these ones in pink and blue and white here, these are going to be our main group elements. They exhibit changes in their structure by losing or gaining electrons, and they receive they give up electrons. Now, if we're looking at this column here with boron, this has 3 electrons that it's willing to give up. It has a valence number of +3, so there's a valence of +3. And that means that this guy will lose 3 electrons to become more stable. Now, when you get into carbon, it's kind of like loosey-goosey, it just depends on the situation. It can either take it or leave it in terms of gaining or losing electrons. And its total number of valence electrons is 4. Now, when we look at nitrogen, oxygen, fluorine in this group, this last column, considered our noble gases, the valence electrons are a little bit different from the actual charge that's denoted in color. The number of valence electrons for nitrogen is 5, but it means that it's willing to accept 3. So it has this -3 designation when it becomes a charged element. Here you have oxygen, and it has a total valence of 6 electrons. And then here with this column with fluorine on down, it has 7 valence electrons. Now this last column is referred to as the noble gases, and with the exception of helium, they have 8 electrons valence, and they don't generally participate in chemical reactions. Now, I talked about this idea of valence electrons. Well, these valence electrons are electrons that are readily available to be exchanged or shared. Now, if they get exchanged, they form something called an ion, and for instances of examples of elements where they have a single element that gains or loses an electron, it will form a monoatomic ion. Now, an ion is a charged particle, and mono just means one atom. And so if we're looking at a monoatomic ion, we're looking at a single element that has a specific charge. Now, it turns out that based on the trends of the periodic table, we can predict what type of ions actually form. Just like the example I listed before with sulfur, you notice that sulfur is in this column here. Now, it has 6 total valence electrons, but when it becomes an ion, it becomes -2. So anything in this column will be -2. Anything in this column will be -1. Anything in this column will be -3. And so the same thing can be said about all the elements. They have a specific charge that's associated with it. But that's not the only type of ion that exists. There is this thing called polyatomic ions that can occur when there are a group of atoms that are bonded together and they have an overall net charge. So what does that mean? Well, you have more than one atom connected. That's why it's polyatomic. And they produce a overall net charge. In this case, this net charge is -2. And so that's an example of polyatomic ion. That's only pertinent because we know that ions can actually later form bonds. And so we're going to look at that in a moment. But before we do, let's take a second and just practice looking at determining the ionic charges of the following. All right, so if you're looking at the ionic charge, you notice that strontium is SR. SR is going to be in column 2, so its ionic charge is going to be +2. If you look at Te, this guy, if you find it on the periodic table, you'll find out its charge is right here on -2. So forth, if we look at nitrogen, we notice that nitrogen is in this column, so it gets a charge of -3. If we look at magnesium, we see it over here for Mg, and that's a +2. And the last one when we're looking for Se, we look on our periodic table. And when it comes down to selenium, we would also see that that one is in the -2 category right here. So that covers that one. So let's talk about what an ionic bond is. Well, ionic bonds occur between a metal and a non-metal. So if you recall from that first slide where we looked at the red and the blue and the yellow, we're looking at the interaction of two different colors, your metals and your non-metals. So you want to be mindful of that because that's how ionic bond, because it's going to be different from how a covalent bond happens. Now there are plenty of examples, but two examples that are listed are sodium chloride, NaCl, and magnesium chloride. And ionic bonds, it's not generally a formal bond, but it's more of an electrostatic interaction. And it's such a strong attraction that we call it a bond between them. Now, when you're writing these ionic bonds, you always want to start with the metal first. The metal you want to come first. Now, let's look at something called a binary ionic compound. And it's basically an ionic compound that contains only two elements. So anytime you have two elements coming together, that's a binary ionic compound. So if you get the vocabulary of binary, binary means two, that's what we're looking at. Now there's a couple of examples. One of them we already saw, which is sodium chloride. The other one here is magnesium fluoride. And we're going to get into in a moment how you actually derive these compounds. Now, binary ionic compounds use their ionic charges in order to write their correct molecular formulas. And if you go back and we looked at the periodic table where we saw these charges that are generated, we can understand that they can participate and they help form the compounds that we know. So the method of doing this starts with something called charge balancing, and there's about 4 steps that are involved when you're writing chemical formulas. It starts with first determining the charge of each ion. You look at an element and then you predict what its ionic charge is going to be. Then you crisscross the absolute value associated with that charge to the bottom right of the other atom. We call this crisscross applesauce, where they're going across. The charge goes to the left and right. Then, if you have numbers that are like or are reducible, you reduce the subscripts so that they have the lowest possible terms. That means if you have a 2 and a 4, you reduce them to 1 and 2. So let's look at one notable example. Here we're going to look at magnesium and chlorine. Well, if you look on the periodic table, magnesium falls in the +2 category. If you look at chlorine, it falls in the -1 category. So we got magnesium and we got chlorine. And so we know that magnesium is +2, and then we understand that our chlorine is -1. Now, we're going to crisscross the two numbers to each other side to understand how charge balancing works. That's why they're being highlighted here in this image. Now, this goes from left to the right. This one goes from the right to the left. And voila, you have the magic of forming magnesium chloride, where the 2 has now gone to this side. The 1, which is understood, has now gone over here. So when you have the formulas like that, they switch one another. Now, if this number was a larger number, you would have to reduce them so that they match pitch. Like, let's say that both of these numbers were 2s. If this was a 2 and this was a 2, they both are 2s, so they simplify to 1. All right, so let's look at covalent bonds. If we look at covalent bonds, we know that they represent bonds between two non-metal groups. And so ionic bonds are metal and non-metal. Covalents are non-metals together. And they share electrons as opposed to having and losing or gaining like ionic bonds. And they both need the electrons to become stable, so that's why they share them. And it turns out that they can form sometimes single, double, or triple bonds. Now, there in all are a few major types of bonds, and we've covered 3 of them, and that's really the extent of what we want to focus on. But I'll recap all 3 just so that we're aware of them. The 3 types of bonds that stick out are ionic bonds, metallic bonds, and covalent bonds. We talked about ionic bonds and covalent bonds, which are a huge focus. And the difference is that ionic bonds transfer, and then covalent bonds share their electrons. So now let's look at some examples to understand whether they're covalent or ionic and better understand how they relate to one another. All right, so we're looking at example number 1. Example number 1, we see that carbon, a nonmetal, is bonded to oxygen, another nonmetal. So because they are bonded together, they form a covalent bond. Now, if we look at the next example, we have aluminum bonded to this guy here. This is aluminum, and we don't really know what this is, but we should know that it's polyatomic as an ion. Now, it's a polyatomic ion, and you have aluminum. This aluminum is a metal. These both are nonmetals. So if you understand the relationship between them, an ionic bond is a metal and a nonmetal that bonds together. So we know that this is an ionic bond. Now, if we look at the next one, this is carbon tetrachloride. It has a carbon that's bonded to these 4 chlorines. This is a nonmetal. This is a nonmetal. Even if I don't know what the structure looks like, I can conclude that it is a covalent bond because it is a nonmetal and a nonmetal. Let's move on. Here we have sodium oxide. And we know how we got sodium oxide because the -2 charge of the oxygen and the +1 of the sodium crisscross. Now, sodium is a metal and oxygen is a nonmetal. So we know that together they come together to form a ionic bond. Now let's look at this last one. This last one is a little bit complicated, but don't get lost. It's got this item here, which is a metal, and this is a group of nonmetals. Metal, nonmetal, I'm seeing a trend. What is that? Oh, an ionic bond. So we've looked at each example as metal, as ionic and covalent, and we're going to look at the number of atoms. We need to understand how many are associated with. This means there's 1 carbon and there's 2 oxygens. This means there's 1 aluminum. This means there's 3 nitrogens. This means there's 9 oxygens, because this 3 outside the parentheses multiplies that. 1 carbon here, 4 chlorines. This is 2 sodiums. This is 1 oxygen atom. This is 1 of the manganese atoms. And there are 7 of this entire atom, but altogether there are 7 nitrogens and 21 oxygens, because the 7 is multiplied here and multiplied there. And that completes our overview of ions, ionic bonds, and covalent bonds as it relates to the lab activity. Good luck.